So a review of some of our Physics 11 concepts. Kinematics is the unit we just finished. D equals VIT plus a half AT squared. VF equals VI plus AT. Kinematics is the study of how things move. If I throw something to you, catch. Kinematics is the study of how things move. Dynamics is the study of why things move. And the reason things move is forces. Kinematics is how things move. Dynamics is why things move. Put your pencils down, look up. This one I am going to pause. So dynamics is the study of why things move. Why do things move? Forces. And so it brings us to a question, Cole. What's a force? Well, last year I told you a force was a push or a pull. That's a terrible definition. It's a bad definition. A physicist would say a force is an interaction between two objects when they exchange. You can dive down to a quantum level all the time, but we're not going to bother doing that. But I am going to point out that probably a force is a push or a pull is a bad definition, but it does work. It is a vector. It matters which direction you push or pull things. The way we described it was who's winning, who's losing. That had to do with which direction things were. It's measured in units of newtons. Because F equals what? MA. We also said a newton must be a kilogram meter per second squared, because MA. Forces are based on interactions between two objects. Now what that means is not only forces come in pairs, it means if you had an object in deep space by itself with no other gravitational fields around, no planets, no stars, nothing, then that object cannot experience a force. A force has to be an interaction between two objects. Some important forces that we're going to study will include the following. These are some that we did last year, so you might remember these names. Who remembers what we called the Earth when it was pulling on all objects downwards towards the planet's center? What did we call that force?
Gravity.
What we call it? Someone said it. Gravity. And Braden, what was the equation to calculate it? What was the symbol? I usually used F and a lowercase g. What did we call the force that could be described as the microscopic hills and valleys between an object and a surface that interlock and prevent or impede sliding? That's the fancy term for friction. And my abbrev for friction was FFR. I don't know why I put the R there. This is probably the only time in my life that I write an extra letter. If you take physics in university, or if you look at a textbook, they'll always just put an F there, but it's a habit that I can't break. I just always put the R there, sorry. What did we call when a surface pushed up on an object to prevent that object from sinking into it like quicksand? Or when a wall pushed sideways on an object to prevent an object from sinking into the wall like quicksand? What force was that? We called that the normal force. Symbol Fn. By the way, look up, don't write this down. Going back to gravity, does anybody remember another name for the force of gravity? It was a single word. No, now was the dumb joke I always said afterwards. Start with the letter W. Okay? Another word for the force of gravity is your weight. Your weight is measured in newtons, not kilograms. So don't write this down. Some textbooks will use a big W for the force of gravity, for weight. The problem with that is W is also west. As a unit, W is also watts. As a physics concept, W is also work. So I'm going to use FG. Some textbooks, don't write this down, will use a capital N for normal force, but that's also north and newtons, and so I'm going to use Fn. But then here is where I'm inconsistent, and I need to apologize. I'm doing bad teaching here. What do we call the force from a stretched string that was constant throughout the entire rope or string? Yes, tension. And here is where I'm bad. I used a capital T for tension. I really should use F with a lowercase t. In Physics 11, it doesn't come back to bite me, but in Physics 12, it will, because a capital T actually is used for something. A capital T is the symbol for the period of rotation. And there is an equation coming in your future where you're going to have tension and the period of rotation in the same equation, two T's that aren't the same thing. And so I'll probably switch to FT for that equation, and I really should just teach it because I'm consistent everywhere else. I don't know why I use a T for tension. And I keep meaning to change that in my teaching, Cole, but I don't know, I'm getting old. Who remembers what was the contact force from an external agent, usually coming from off the page? Sometimes it was a person, or often I said, and maybe it's a little invisible leprechaun, I don't care. Something was creating a force from off the page. Remember what we called that force? Applied. There you go. We called it the applied force. And I usually wrote that as F. Really, that was my way of saying, look, something is pushing or pulling on this object. I don't want to make up a story telling you what it is. Just assume there's a force there. What did we call the force of resistance from the air that always acted in the opposite direction of motion? Now, one thing we called it was air resistance, and we still will, but that was a fancy schmancy name. Does anybody remember? 4 letters, starts with a D. Drag. But I'll usually write it as F air, but you can write F drag if you want to. I think there is actually a symbol for drag, but I can't remember. I think it's a Greek letter. Have I mentioned we're running out of letters? The last one was not a force that appeared on our free body diagram. Instead, it was the vector sum or the resultant of all the forces acting on an object. In fact, when I told you that F equals what, MA, really what I should have said was F this equals MA. What do we call the vector sum of all of the forces acting on an object? Yeah, net force. And in fact, winner minus loser equals F net, which means F net doesn't show up on the free body diagram. What shows up are the winners and the losers. But when you add them all together vectorially, and this year we will have stuff that's at right angles and have to do components and things, the net force is the vector sum of all of them. F net equals MA. I went on a big rant last year about Sir Isaac Newton and his 3 laws of motion, how he overturned thousands of years of thought and said, no, you're all wrong. I can explain how everything in the universe moves with 3 laws. Newton's first law, often called the law of inertia, often is phrased something like this: objects at rest tend to remain at rest. Objects in motion tend to remain in motion, which I've always thought was confusing. Here, I stole this one from the internet. Every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied to it. Here's what it says. The only way that you can accelerate an object, or change its velocity, because that's what the definition of acceleration, is to apply an unbalanced outside force. If an object is accelerating, you know forces are not balanced. If it's not accelerating, you know forces must be balanced. Oh, and it works backwards. If you know forces are balanced, then you know it can't be accelerating. If you know forces aren't balanced, you know it must be accelerating. This is often called the law of inertia because we introduced the concept of inertia as that thing that resists a force. And we said to you, if you want to know what inertia is, we're going to pretend it's mass. So if I want to move a feather, if I want to accelerate a feather, I can blow on it. A feather has so little inertia, so little mass, that a tiny force can change its motion. If I blow on a locomotive, will I change its motion? No, it's got way too much inertia. way too much mass. And then last year during relativity, I said I lied. Mass and inertia aren't the same thing, because as you get closer to the speed of light, your inertia increases. But for now, as long as we're not going near the speed of light, Calvin, you can say that mass and inertia are the same thing. You can measure inertia in kilograms. So in outer space, if you give an object a push and then walk away, as long as there's no other gravitational fields, as long as it doesn't get caught in another planet's gravity or another star's gravity, that object will keep going forever. That's what our Voyager probes are doing. We gave them a big enough push to escape the sun's gravity, and we've let them go, and both of them have exited the solar system, and they will keep going forever until the universe ends. Unless hundreds of light years from now, they happen to get pulled into the gravitational field of some other star or planet. But if that doesn't happen, they're going to keep going in a straight line at a steady speed. That's Newton's first. That's how all objects behave in outer space. Oh. Put your pencils down, look up. I think I showed you this one last year. So who remembers, what force is it that makes cars stop and go? What do cars need in order to drive? Friction. Friction. It's not tires, it's not motor, it's friction. Here with this ice, there's no friction, so these cars are going to behave like they're in outer space. They're going to go in a straight line at a steady speed until an unbalanced force is applied to them. Oh, change direction, there was a force. Change direction, an unbalanced force is applied to it. Okay? But now it's going in a straight line. Newton's first. This one is interesting. If you watch, the front left tire is all of a sudden going to get some friction and it's going to stop. But the rest of the car is going to keep going in a straight line at a steady speed. You'll actually see it pivot right around the tire. Newton's first is going to kick in here. Okay? So that front tire got some grip, but the rest of the car, they stopped. They should have cut their losses. They should have been happy. Pardon me? Portland, Oregon. About 10 years ago, maybe 12 years ago. Now, if you're watching really, really close, you might notice, Mr. Dewick, these cars are actually speeding up. It's actually, yeah, there is a tiny bit of a hill, and it's just enough of a hill that gravity is overcoming friction and causing them to speed up a tiny bit. So this isn't perfectly Newton's first, but it's close. It's going to get some grip right here, right where that little manhole cover or open area was. So there was enough friction there to bring it to a stop. So Portland gets weather similar to what we do. They don't get much snow. Same way Lower Mainland, we don't get much snow, and we don't know how to drive in it very well. You may have noticed last week, much of the U.S. had big cold weather, and I'll try and find it on YouTube. Someone released security footage from their security cam, and there's a pickup truck sliding sideways down the road majestically at a steady speed, just not enough friction to hold it in place, and Newton's first. It's quite majestic. Or maybe the pickup truck had enough and just decided to get out of there, right? Did they change direction? Yes. So was there an unbalanced force acting on them? Because they did accelerate, not by speeding up or slowing down, but by changing direction. So they either have better tires, or maybe right there was enough friction for them to make that corner. It's interesting. Why can the fire truck drive when the cars can't? Physics 11s who had me last year. What? Why would the mass help? How does it increase friction? So now, and I haven't taught you that, we did this last year, but it's been a while. Who remembers friction is what times what? U times the normal force. So remember, the normal force is how hard the ground has to push up. Does the ground have to push up harder on a fire truck or on a little mini fire truck? So that's why in snow, often large trucks or buses, they can drive a little better in the snow, although there's also limits, especially when it comes to hills. SFU's hill is notorious that buses can't get up the hill to drop kids off at SFU, okay? So I showed you that one last year, and then I think I showed you this one. Somebody is Parson Brown. He'll say, are you married? We'll say no, man. But you can do the job when you're in town. Later on, we'll conspire as we dream by the fire. Must have been sorry, guys. I just started the plans that we made. And I showed you that one last year, and we laughed, but I also got really serious on you, and I said to you, if you're ever skidding, stay in your car. You have an airbag, you're surrounded by a roll cage and a crash cage, you're surrounded by padding on your seat. I think I told you every year this happens, people are panicking. This person is panicking. They don't know what to do. They're not thinking clearly, and they've gone back to when they were 8 years old to stop their bike in an emergency. They put their feet on the ground, and I've told you people do this. He's lucky or she's lucky that they didn't slide underneath the vehicle, right? So stay in your vehicle. Also, you don't want to be playing on this road right now. This person almost dies. And you can see this panicking is not that uncommon. It happens fairly often. One that I didn't show you last year, here's a lovely example of Newton's first. So this is a trapeze and a net, and we're going to land. And the leaves have enough inertia that they remained at rest because no force was applied to the leaves until the mat bounced back up again. Okay. Then we looked at, space station was another great example. So here is the space station being reboosted.
Here we are at the International Space Station. We're doing a reboost right now, and we're showing that the space station is actually accelerating away from us.
So the space station isn't completely in vacuum. It's above most of the Earth's atmosphere, but it is grazing the Earth's atmosphere, and so it gets slowed down slightly, and so we have to do a reboost every so often. And so, Kevin, right now, the space station is accelerating out of the screen towards us. So they're firing their rockets, and what you're going to see is if the astronauts lift their feet up, it's going to look like they're moving backwards. Actually, no, they're staying at rest, and the space station is accelerating towards us.
We're going to float in the middle of the cabin, and it started already. We start off stopped in front of the camera.
By the way, somebody asked me this in my other blog. Mr. Duick, why are their faces looking so red? You will always, on the International Space Station, the astronauts' faces will look red because on Earth, your heart is always having to pump against gravity to push blood to your face, and it's just used to that. That's how hard it's going to pump the blood to your face. No weight on the International Space Station, and so they have a red face. They also typically will have a stuffed nose because your nose gets cleared by gravity, and so while you're on the International Space Station, all the food tastes weird, the same way as when you have a cold and you eat food, often things taste a bit off. Somehow they have that the whole time there. But then they can fly like Peter Pan, so there's a, trade-off, right?
And you can see, and we get moved. The space station's accelerating, leaving us behind.
So they're not moving backwards, they're at rest. Wow. The space station is accelerating forwards. And so because they're at rest, Newton's first, they're staying at rest.
Ooh. That's amazing. I'll do it again. Okay. Floating still. Oh! Wow! Wow! Oh!
And then the other one that I did with you all last year was I put the big jug of water under, and I put a piece of paper towel underneath it, and I had somebody lay down. Was it somebody here that I had laid down? Was it one of you that I had volunteer? Quote, volunteer. And I yanked the paper towel out, and the person stayed dry. Remember doing that? It's the dishes underneath the tablecloth from underneath the dishes. Okay? So I'm not going to redo that one, but I did that one last year. Newton's first. Unless there's, you know what? Let's keep going. Newton's second law is the equation. It's the mathematical relationship between force, mass, and acceleration. It says force equals mass times acceleration. Newton never actually published it that way. He was much more interested in acceleration, so he wrote it as although he didn't write it that way either, he wrote acceleration in a different way. He was much more interested in something called impulse and change in momentum. But the simplest version is F equals what? ma. That's on your formula sheet, but you'll all end up memorizing that one because you're lazy and you'll get sick of looking it up. Newton's third law is often called the law of action-reaction. It's usually stated something like, for every action there is an equal and opposite reaction, which I've always found confusing. What's Mr. Dewick's version? Forces come in. I'm going to add one more word. Instead of forces come in pairs, I'm going to say they come in opposite pairs. Or as an equation, the force of object A on object B is the same as negative the force of object B on object A. If I push Diego 10 newtons south, Diego has to be pushing back on me 10 newtons north. Forces come in pairs. And I'll feel that through my hands when I push you. Okay. Nice example of Newton's third law. And a little bit of Newton's first.
Patrick Frischer is gearing up for his big jump. And what's he jumping over? This large pile of loose dirt.
I called some of my friends and said, hey, I think I might try this. Why don't you come by and see if it's at all possible?
Wow, sounds like he's really thought this through.
I don't think he's gonna do it. I got 911 ready.
With friends like these, how could he possibly fail? The amateur daredevil revs up and takes off. Pat is going roughly 60 miles an hour when he hits the dirt with his wheels.
Let's pause. So let's look at the physics of this. First of all, the motorcycle applied a force to the ramp. Forces come in pairs, so what does the ramp do? Applies the force back on the... So the motorcycle is going to slow down. Is Patrick attached to the motorcycle? No, Patrick is experiencing Newton's first law. He's continuing to move in a straight line at a steady speed. And then I think I told you there comes a point when the universe wants to teach you a lesson. When the motorcycle lands on top of him, that's the universe saying, don't be dumb.
Then his head.
The dirt was real loose, which caused my tires to get in the jump and launch me over the handlebars.
So what What does Pat think of his momentous jump?
I know not to do something like that ever again. It was just stupid to begin with. It's still stupid now.
But Pat has some words of wisdom for his fellow teenagers.
Think more before you do stuff.
Good advice.
Yeah. Okay, so let's take what we know of Newton's laws. And again, to my 2 new students, I spent 3 lessons on this in Physics 12 and Physics 11 as opposed to 10 minutes like I've just done now. So if you're finding this tricky, you're not alone, don't panic. But for the rest of us, why would an athlete want low mass shoes, especially if you're in the 100-meter sprint, let's say? Why would you want your shoes to have as little mass as possible?
Have more acceleration.
How would that work? You know what? Let's get the A by itself. F equals what? So A equals... Let's write that down. So as m gets smaller, that's an arrow pointing down, what can you tell me about your acceleration if the force stays the same? If you divide your answer by a smaller number, if you divide by a smaller number, what happens to your answer? As m decreases, F increases. Yeah. Okay. You're not going to wear big clunky hiking boots in a 100-meter sprint. What if you were working on the International Space Station in 0G? Would it hurt to get hit in the face by a moving object while in 0G? No? Convince me. You know what this is really saying? Would it apply a force? Because if it applies a force, it'll hurt. You okay with that? Okay. In outer space, do objects still have mass? So, we have mass. When it hits your face, would its velocity change? I'm going to ask you the same question. I want the same answer. I'm just going to phrase it differently. When it hits your face, would it accelerate? So if we have mass and acceleration, we must have a force. So, sorry, Alec. Yes, it would hurt. Here's what else that means. That means you can use a hammer in 0G and it will still hammer a nail in. Even though there's no gravity, they still have mass, the hammer still has mass, and it will accelerate, decelerate when it hits the hammer, so it will, when it hits the nail, so it will apply a force. Okay? What was that? What do you mean? You're asking a good question. Elaborate. You would feel probably a bit more of a recoil force. Have you hammered a nail in before? Okay. Normally, you're hammering straight down. And so the recoil force that the nail applies is mostly canceled out by gravity pulling down on the hammer. But you could get a better indication of what it would be like if you tried nailing while laying on your back, nailing something into a ceiling. You would find, oh, after I hit the nail, I'm having to exert my wrist way more to keep this hammer from hitting me in the face. Okay? And it's not, it's always been there, actually. It would be the same as in 0G. It's just typically you're either hammering straight ahead into a wall, but more often than not, you're hammering down and you don't notice the advantage that gravity is giving you. It's helping you along. Is that okay, an answer? Speaking of gravity, a force with which you have had some experience is the force of gravity between you and the earth. This force is also known as weight. Weight is measured in newtons. Mass is measured in kilograms. Weight is measured in newtons. If you tell me your weight is 42 kilograms, no, it's not. Or pounds. So the equivalent of newtons in the old imperial system, pounds, is the unit of force. So it is correct in terms of physics to give me your weight in pounds. It would not be correct to give me your mass in pounds. Does Does anybody know what the units for mass are in the old imperial system? This is why the old imperial system is so stupid. Okay? Also tells me that nobody bothers reading ahead. Force of gravity is not the same as mass, although they are related. Mass is the amount of matter in an object, measured in kilograms, or slugs in the old system. Yep. To relate mass to force, we need to know the number of newtons of force per kilogram of matter. Draw a little line down the middle of the box. Braden, you already told me. How do I calculate the force of gravity? mg. What that means is little g can be thought of as how many newtons of force on every kilogram of mass. That's called the gravitational field strength. So, sorry for those of you on YouTube, but I have here a little spring scale, and I have here a 1 kilogram mass. What's the force of gravity on a 1 kilogram mass? What's 1 times 9.8? Which is really close to what nice round number? So if I hang this on here, you should see a little less than 10 newtons. It might be a bit off because the spring scale is old, but you should see between 9 and 10 newtons. Okay? The reason objects fall or accelerate at 9.8 meters per second squared is because the Earth pulls on every kilogram with 9.8 newtons of force. And if you get the A by itself in the force equation, F over m, if you're pulling on 9.8 newtons of force on every kilogram, you'll accelerate at 9.8 meters per second squared. So the reason G is what it is because Earth has a gravitational field strength of 9.8. If we were on the moon, it'd be right just less than 2. If we were on Mars, it'd be a little above 3. And so one way to measure the gravitational field strength of a planet is to take a spring scale, hang a known mass, and figure out how many newtons are pulling on it. Now, there's another way that we'll learn later on, I hope, this year. I hope to get to it, where I'll show you, if you know the mass and radius of a planet, you can figure out what the gravitational field strength is before you land on it, because we had to do that when we went to the moon. We had to know how strong to build the rockets before we landed the rockets on there. Otherwise, it wouldn't have done us much good. So, another word for the acceleration due to gravity, 9.8 meters per second squared, is gravitational field strength. And in fact, gravitational field strength is why the acceleration due to gravity is what it is, because the gravitational field strength tells you how hard that planet is pulling on each kilogram, which will make it accelerate. Got that? Different way to think about little g. Different way to think about that 9.8. Thinking of it as a force per kilogram instead of a meters per second squared. So, example 2 says, find the weight of a 10 kilogram object on the Earth or on the moon. When it says find the weight, it's asking you to find the force of gravity. So I'm going to write Fg equals mg Earth and Fg equals mg moon. Diego, what's the mass that they gave me in example 2? And what's G on the Earth? Good old. And we're not going to put the negative in because you'll see why. But yeah, we're going to keep things kind of scalarish. In your head, Diego, can you go 10 times 9.8? 98. In other words, if you pick up 10 kilograms, you're exerting 98 newtons of force. Now compare that with on the moon. What's the mass on the moon? Still 10. But Diego, what's G on the moon? Look up. About 1.6. What's 10 times 1.6 in your head? Okay. So the astronauts, when they walked on the moon, they were wearing spacesuits that on the Earth weighed about 300 pounds. On the moon, 50 pounds. The mass didn't change, but that's why they were more functional. In fact, if you watch, you can do a YouTube search, you'll realize because the spacesuits are very awkward and bulky, the astronauts figured out very quickly the best way to walk on the moon was to do little hop skips. They'll do little hops, and they get the giggles. There's a video, you'll see an astronaut singing to himself, strolling on the moon one day, and he just starts laughing because he's 8 years old and able to jump so high, and they're trying to be serious scientists, but this is so cool. Okay, so your mass doesn't change even near a black hole. Your weight is what changes. Your weight is location dependent. Is that all right? Turn the page. We get to vote again. Okay. So here's our thought puzzle. If the force of gravity acts on an object, then the object A remains at rest, B moves at a constant speed, C accelerates in the direction of the force, or D, all of the above. If gravity is acting on an object, then the object A remains at rest, B moves at a constant speed, C accelerates in the direction of the force, or D, all of the above. Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of your answer. Who says, Mr. Dewick, A, when gravity acts on an object, it remains at rest? A. No one. Huh. Who says moves at a constant speed? Was that a vote, Braden, or you were just adjust? Okay, because that could have been a very smooth, I'll vote, but no one will notice? Okay. Obviously, C accelerates in the direction of the force. C. Got 1, I got 2, I got 3, I got 4, I got 5. I'm waiting. Is that a vote? No. 5? Okay. D. Convince me. Convince me. Austin, what did you vote? You D? Convince me. Can you give me an example of how A could be true? By the way, D is correct. Okay? So, for D to be correct, that means I should be able to tell you an example of A and B and C. Can you give me an example of how gravity can be acting on an object, but it can remain at rest? Yeah, cool. Oh. Okay, so person sitting in chair. Is gravity acting on all of you right now? Yeah. Are you accelerating? Okay. Can you give me an example of how gravity could be acting on something, but it could be moving at a constant speed? Yeah. What's the fancy word when air resistance exactly cancels out gravity? Start the letter T. Something velocity. Like a parachute. Okay, when I pulled my parachute after I jumped out of an airplane, I mentioned I jumped out of an airplane, I hit terminal velocity. Can you give me an example of how C could be correct? Okay, in free fall before terminal velocity. So since I gave you an example of how A could be true, and B could be true, and C could be true, Elias, what's the correct answer? And I would take that as a test. Now, because I gave this into your notes, it's unlikely that I give this one to you on a test, but I would accept that if it was a test question. I'd say, yeah, great answer. You've convinced me. So Newton's first law says that if we have balanced forces, Objects at rest remain at rest. You know what? If we have balanced forces, if forces are balanced, A equals 0. If forces are unbalanced, A cannot be 0. And it works backwards. If A is not 0, forces cannot be balanced. If A is 0, forces must be balanced. They must cancel out. Now, more and more, instead of balanced, you're going to hear me say the net force is 0. Because that's really what we're saying. F net, or does anybody know what this funky little E symbol means?
Energy.
No. It's a Greek letter sigma, but what does it mean in math? The sum of, or the total. So the total force, or the total force, the net force, or the net force, we say this: F net equals ma. And the direction of your acceleration determines the direction of the unbalanced force. Or if you know the direction of the unbalanced force, you know the direction of the acceleration. They work in both directions. Also, little note that both of these are the same, because I can write A equals F over m. That's definitely newtons per kilogram, but you learned last year that acceleration is meters per second squared, so they must be the same units, newtons per kilogram and meters per second squared. I usually use newtons per kilogram if I'm finding the acceleration this way. I usually use meters per second squared if I'm finding the acceleration using velocities and times. But I don't care which one you use as your unit for acceleration. I'm not going to be fussy. But what it does mean is another term for the acceleration due to gravity is gravitational field strength. And that's measured in newtons per kilogram. So what's the acceleration due to gravity? 9.8. What's the Earth's gravitational field strength? 9.8 newtons on every kilogram. 9.8 newtons per kilogram. And that's why objects will accelerate at 9.8 meters per second squared. So that's some theory. Now let's start to apply this. Example 4 says, find the unbalanced or net force in each situation, include direction. So I'm going to put a little compass rose right here. Okay. Justin, what's the net force on object A, magnitude and direction? Be fairly obvious. 2 newtons at east. Yeah. Elias, what's the net force in object B, magnitude and direction? Jasmine, what's the net force on C, magnitude and direction? Yes. And this n is newtons, this n is north, and I know that because there's a little at symbol there. Again, we're running out of letters. Good. Ooh. Austin, what's the net force in D, magnitude and direction? Yes. And what you're really doing, Austin, is you're doing what I called last year, winner minus loser. You let one way be positive and you let one way be negative, and you were clever enough to say, I'll let the positive direction be the biggest one, so that instead of going 3 minus 8, I'll go 8 minus 3. Yes? You did all that intuitively. Good. Ooh, Alex with an X. What's the north-south net force in E? What's the north-south net force in E? Not 2, 0. Now here's what that means. That means in terms of north-south or up-down, either this object is not moving north-south at all, or it could be moving north or south at a constant velocity. That's all I know is A is 0. I don't know that it's at rest. I know it's not accelerating. What is the net force on this magnitude and direction? Ooh. How would I calculate the net force in F? Who's winning?
Why?
Because I asked you to. Who's winning? Okay. So again, then, for those of you that had me last year, how would you calculate the net force? More specific in this question. Yep. Keep going. Y minus Newton's direction. Which way must this object be accelerating? Yeah. I will start to occasionally give you questions with no numbers. But I'm going to argue it's the same physics I taught you last year. And actually, to me, no numbers makes it easier because there's no way I'm going to make a dumb math mistake. It's a little more intimidating at first, but when you really start to think algebraically, so much easier. It's why I taught you formula manipulation last year instead of having you plug numbers in. There are some teachers just have the kids put numbers in right away, and you solve it like a Math 8 equation all the time. Let's be better than that. Do ourselves a favor. All right. So to solve force problems, here's what I taught you last year. We're going to use something called a free body diagram, or FBD. We're going to show each force with an arrow. We're going to draw the arrows roughly to scale. And what I mean, Kevin, by roughly to scale is if they're the same size, I'll try and make them about the same length. If I know one force is larger than the other force, like in this diagram, I'll make the arrow clearly longer so it's obvious to me. My friend, I bought these notes from the physics prof at Kwantlen. He also has students put acceleration and velocity on his free body diagrams. He uses a wiggly line for acceleration and he uses a dotted line for velocity. I like my free body diagrams pristine, so I only put forces on them. That's just me being me. And then we use a tug of war analogy. And what was the tug of war analogy that I gave you last year? I said, we're going to ask who's winning, which force is bigger, and we're going to go winner minus loser equals F net. Wait a minute, everybody cross out F net, MA, because F net is MA. We're going to go winner minus loser equals MA. But that A is the net acceleration, the overall combined replaced with a single acceleration. And this allows us to avoid having to decide ahead of time which way is positive and which way is negative. Positive will be whatever makes the math the easiest. So we will no longer put a negative 9.8 in. We'll just put a 9.8 in whenever we're doing an acceleration for gravity. So let's do a couple of questions. Let's do example 5. I like example 5. I like example 5. I like example 5 is a nice question. Example 5 says this. A 2,000 Newton rock hanging from a rope accelerates upwards at 3 meters per second squared. A says, draw a free body diagram. I'm going to do that right here. I'll represent the mass with a dot. And then I taught you to go very systematically. I said, resist the temptation to try and do the toughest, most mysterious force right away. If you go systematically, it'll become clear. So here's what I taught you last year. I would have said something like, what are the forces acting on this rock? Get the obvious one. Whenever I say get the obvious one, which one do I mean? So let's have FG pointing downwards, gravity. What else? Which way is this rock accelerating according to this question? Up. Which way must there be a bigger unbalanced force pointing according to Newton's first? So I know there's a bigger force pointing up. I'll exaggerate it so it catches my eye. Which force is that? the rope, and what name did we give to the force from a rope or a cable? Tension. So I'll label that with a T. There's my free body diagram. Okay? B says compare the forces that act on the object. We did with our arrow lengths. Which one's bigger? Must be T. C says write a net force equation. And so we said our template is always going to be winner minus loser equals MA. Who's winning? Who's losing? What's that equal? MA. Then D. What do they want me to find? How would I get the T by itself? Plus the FG over. For part D, here's my tension equation. Tension equals the force of gravity plus MA. Or MA plus the force of gravity. You're adding, so who cares what order you write it. Now this question, I stuck a mini curveball in. Don't panic. Let's see if we can solve this. Tension equals, what's the force of gravity? I'm going to say, first of all, that's two bad guesses. 9.8 is not a force. What is 9.8 a measure of? Not a force, but what? Acceleration. Don't ever tell me an acceleration is a force, because it's not. And are we going to put the negative in this unit? No. So I ask you again, what's the force of gravity? The answer is, I told you. Yeah. The answer is, I told you. You all know the force of gravity already without your calculator. 2,000. How do I know that's a force? What are the units right next to it? I gave you the weight, not the mass. And I will do that sometimes this year. So I don't even need mg, Emma. I can just say, you know what the force of gravity is? It's that. Plus. Oh, and what's the acceleration? What's A? I told you in the question. So there is going to be a 3 here. What's the mass? I didn't tell you that. Or did I?
Yeah.
If I know the weight, how do I figure out the mass? And I'm so lazy, I'm just going to go 2,000 over 9.8. I can get the mass from any force by dividing by 9.8. I can get the equivalent mass in kilograms if I'm lifting it. Which is what? How big is tension? It can be around 2,600 something. I can do that much in my head. 2,600 and I'll go 2610. I'll go to 3 sig figs. Okay. How big was the force of gravity in newtons? 2,000. How big was the force of tension? 2,610. Hey, Alec, we get to vote again. So, example 6. Is it correct to say that if the rock in example 5 is moving upwards, tension must always be bigger than gravity? True or false? So we got an answer for tension of 2,610. Gravity is 2,000, the weight. Is it correct to say that if the rock is moving upwards, tension must always be bigger than the weight? Time to vote. Who says, yeah, clearly we just proved it. True. True. 1, 2. 1, 2. Oh, Elias, check it. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ooh, this might be our first almost 50-50 split. Who says false? I'm going to count. 1, 2, 3, 4. Some of you didn't vote. I know who you are. Convince me. I disagree. You ready?
Do it.
Can you be moving up at a constant speed? What if A was 0? What would happen to this MA right here? What's M times 0? And I would get tension equals gravity, which means tension doesn't always need to be bigger. It can be equal. Yes? Yes? Okay. So I just showed that we can be moving up and tension can be equal to gravity. Example 7. Can we be moving up and have tension be less than gravity? Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. So, is it possible for tension to be less than gravity? Who says, yeah, it's totally possible for tension to be less than gravity? Totally. Is that a hand up? Okay, got 4. Who says, no, it can't? Some of you aren't voting. I'll call you on it soon. Convince me. Yeah. What are you defending? Yes or no? Yes. I agree with you. What? So, moving up but slowing down. What direction, if you're moving up but you're slowing down, what direction are you accelerating? Okay. A must, lowercase a, Mr. Dewick. A, stop doing that. Accel must be down. If the acceleration is pointing down, which way is the winning direction? Same answer. Yeah. Winner is down. So gravity is winning. Bigger than tension. Yes? Gotta be. Okay. So, oh yeah, you've been waiting for this day. But by the way, have I convinced you for these? Yes? Okay. And for all of you that picked the wrong answer, I know why. It's so easy to confuse velocity and acceleration. I don't care which way we're moving. For force questions, I'm always asking which way are we accelerating. And I was sneaky because I kept using the word moving in the question. I never in the questions said accelerating. I was very careful. Okay? Moving upwards. Moving upwards. Doesn't mean you're accelerating upwards. Constant speed, then the forces are balanced. They have to be. Slowing down, well, then gravity's got to be bigger. Tension's smaller. Yeah? Okay. Next page. I wrote this out. I'm just going to summarize. This basically says we're not going to let down be negative all the time. We're going to let positive be whichever makes the math nicer, which means sometimes, especially for a question like this, we'll probably let down be positive, not negative. We have to go to my tricycle. And I will pause the video. This may be my favorite demo. What I assigned the Block E kids. Yeah, I love that tricycle demonstration. And those of you on YouTube are going, what tricycle demonstration? Sorry, got to be in my class. Number 1 is good. Now, number 1 is a review from last year, but I'm jumping into the deep end already. So if you're stuck, I'll happily go over this tomorrow in class or during a blended or whatever. Number 2 is good. Circle 1, circle 2. I like number 3. Number 3, no numbers. I told you more and more this year, I'm going to give you a question. So here's what number 3 says. Assume force F is the only force on the block. If the first block of mass m with force F accelerates at A, what will the same force F accelerate 2m at? You can make up numbers if you want to and try and spot the pattern. Oh, I'll let force F be 12 newtons. I'll let m be 5 kilograms, and I'll figure out what happens. Or you can try and do it algebraically. Stay off your phone, Alec, for a bit longer, please. Thank you. So 3 is good. 4, 5, and 6 are good. 7 is good. But you can skip 8, 9, and 10. 11 is good. 12, 13, 14, 15. 12, really, 11, 12, 13, 14, and 15, you're not really going to be showing any work. It's conceptual stuff, so it's not like you have to doll or anything like that. I just want to see if you can figure out the correct answer and have your aha moment. Okay? My angels, is about half an hour, a little more than half an hour left. Thank you for your patience. That was a lot of me talking. The rest of the class is yours.